Parametric equations have several benefits that become clear if we apply them to real-world problems. Let's consider how to model the path of a projectile. To model the path of some projectile, we use two parametric functions. We do this because each function will give us a coordinate of the location of the object. The function x of t equals the quantity of v0 times the cosine of theta, all times t, will give us the x value of the object's position, or the horizontal distance the object travels at a certain time. The function y of t equals negative 1/2 times g times t squared plus the quantity of v0 times the sine of theta, all times t, plus h, will give us the y value of the object's position, or the vertical distance of the object at a certain time. In the second equation, g accounts for the effect of gravity on the object. Depending on the circumstance, we can use either g equals 32 feet per second squared or g equals 9.8 meters per second squared. To solve either equation, substitute the known values. To find the horizontal distance, substitute the initial velocity in for v0 and substitute the angle in for theta. To find the vertical distance, choose the appropriate value for g and substitute it into the formula. Then substitute the initial velocity in for v0, the angle in for theta, and the height in for h. Let's look at a problem where we can apply parametric equations to a real-world problem. First, we'll want to organize the information given to us. We know we need to find h, v0, and theta. We also need to decide on the correct value to use for gravity, g. Let's look at the information to see what values we need. In this problem, Angela is launching her toy rocket off her back porch, which is said to be 10 feet above the ground. This means we have h equals 10. We're told the rocket has an initial velocity of 51 feet per second, so we can set v0 equal to 51. Since the units in the problem are given in feet per second, let's use g equals 32 feet per second squared. The angle to the horizontal is said to be 63 degrees, so let's set theta equal to 63. Using all of this information, we can set up our equations. Our first function is x of t equals the quantity of the initial velocity, in this case 51, times the cosine of theta, which for us is 63 degrees, all times t. Our second function is y of t equals negative 1/2 times g, which we can rewrite as negative 16 times t squared plus the quantity of the initial velocity, so in our case 51 times the sine of 63 degrees all times t. Then at the end we add the height, which is 10. Now that we have our equation set up, we want to find where the rocket is after 3 seconds. So we'll substitute 3 for t in the first equation and solve. So we have x is approximately equal to 46.31 feet. Now let's do the same for the second equation. After simplifying, we can see that y is approximately equal to 2.32 feet. This means that after 3 seconds, the rocket has traveled a horizontal distance of 46.31 feet and is at a vertical distance of 2.32 feet. If we were to plot this point on a graph, the ordered pair would be 46.31, 2.32. Like the last example, our first step should be to organize the information and define our variables. In this problem, the golfer is standing on a hill with an elevation of 42 feet. In other words, he is standing at a height of 42 feet above the horizontal. So let's set h equal to 42 feet. We are told the golf ball initially travels at a rate of 130 feet per second, so the ball has an initial velocity of 130 feet per second, and we can set v0 equal to 130 feet per second. Since the units in this problem are all given in feet and feet per second, let's use g equals 32 feet per second squared for gravity. Finally, we can write theta equals 15 degrees since that is the angle at which the golfer strikes the ball. Let's set up our equations. In the first equation, we can substitute 130 in for v0 and 15 in for theta. In the second equation, we can substitute 130 in for V0, 15 in for theta, and 42 in for h. We want to know whether or not the golfer will make his shot. To do this, let's set the first equation equal to the horizontal distance between the golfer and the hole, which is 350 feet. Now we can solve for t. So we have t is approximately equal to 2.79 seconds. To find the vertical distance after that time, we can substitute this value of t into the second equation. Now solve for y. In this case, y is approximately equal to 11.32 feet. In other words, the golf ball will still be 11.32 feet in the air when it reaches the distance of the hole, so the golf ball will not land in the hole.